Today we have a quadratic with a known vertex, one additional point, and a request for the sum of its standard form coefficients. The tempting route is to expand everything. We will first find a shorter route, then use expansion as an independent verification.
Here is the exact workbook prompt. A quadratic function has vertex 3, -8, and passes through 5, 4. In standard form, the function is f of x equals a x squared plus bx plus c. What is a plus b plus c?
The source choices are 4, 1, 22, and 7. Since all 4 are small integers, estimation alone will not separate them. We need to connect the vertex information to the exact expression, a plus b plus c.
Separate the information by role. The vertex gives the horizontal shift 3 and the minimum or maximum value -8. The point 5, 4 will determine how steeply the parabola opens. The requested coefficient sum will come from evaluating the function at a special input.
My first thought is to write a x squared plus bx plus c, substitute both points, and solve for 3 coefficients. But one point and one vertex actually encode enough information, and vertex form exposes that information much more directly.
A quadratic with vertex h, k can be written as a scale factor times x minus h squared, plus k to avoid confusing the scale factor with the later standard form coefficient names. Let us call that scale factor capital A.
Our vertex is 3, -8, so h equals 3 and k equals -8. Substituting those values gives f of x equals capital A times x minus 3 squared minus 8.
Now use the point 5, 4. The input 5 must produce the output 4. Replacing x with 5 and f of x with 4 gives 4 equals capital A times 5 minus 3 squared minus 8.
5 minus 3 is 2, and 2 squared is 4. Add 8 to both sides, so 12 equals 4 capital A dividing by 4 gives capital A equal to 3.
We now know the complete quadratic in vertex form. F of x equals 3 times x minus 3 squared minus 8. This form already satisfies the vertex, and the point calculation fixed the only remaining unknown.
Here is the shortcut. In standard form, f of x equals a x squared plus bx plus c. If x equals 1, every power of 1 is 1. Therefore, f of 1 equals a plus b plus c, exactly the quantity the question asks for.
That identity is not a trick specific to this parabola. It follows directly from substitution. Whenever a polynomial's coefficient sum is requested, evaluating the polynomial at 1 collapses every power of 1 and reveals the sum.
So evaluate the vertex form at 1. 1 minus 3 is -2. Squaring gives 4. 3 times 4 is 12, and 12 minus 8 equals 4.
Because f of 1 equals a plus b plus c, the requested value is 4. That matches source choice A. Notice that we found the coefficient sum without ever calculating b or c separately.
There is a beautiful geometric check. The axis of symmetry is x equals 3. The given input 5 is 2 units to the right of that axis, while input 1 is 2 units to the left.
A parabola has equal outputs at inputs equally distant from its axis of symmetry. Since the problem tells us f of 5 equals 4, symmetry predicts f of 1 equals 4 before we perform any additional arithmetic.
We can also verify the vertex itself. At x equals 3, the squared factor becomes 0, leaving -8. So our equation produces the required vertex output exactly.
And at x equals 5, the equation gives 3 times 2 squared minus 8. That is 12 minus 8, or 4. Both pieces of the original context are satisfied.
For a second valid method, let us now expand. First, square x minus 3. Using the binomial pattern gives x squared minus 6x plus 9.
Distribute the leading 3 across all 3 terms. That produces 3x squared minus 18x plus 27. Then the outside negative 8 still must be combined with the constant term.
27 minus 8 is 19. So standard form is 3x squared minus 18x plus 19.
Now the standard form coefficients are visible. A equals 3, B equals negative 18, and C equals 19. Remember that B includes its sign.
Adding those coefficients gives 3 plus negative 18 plus 19. 3 minus 18 is negative 15, and negative 15 plus 19 is 4. The full expansion agrees with direct evaluation.
Compare the methods. Direct evaluation uses the requested expression structure and needs fewer algebraic steps. Expansion exposes every coefficient and gives a strong independent check. On a timed test, evaluate first and expand only if you need verification.
Trap 1 is writing x plus 3 squared because the vertex x-coordinate is positive 3. Vertex form uses x minus, h a factor x minus 3 becomes 0 at x equals 3, which is exactly what the vertex requires.
Trap 2 is treating negative 8 as the standard form constant c in vertex form. Negative 8 is the vertex output. After expansion, the actual constant term is 19. The same number can play different roles in different representations.
Trap 3 is evaluating at 0 because c equals f of 0. That finds only the constant term. The sum of plus b plus c requires x equals 1 because 1 squared and 1 both preserve their coefficients.
Trap 4 occurs while solving the scale factor. From 4 equals 4 capital A minus 8, add 8 before dividing. The result is 12 equals 4 capital A, not 4 equals 12 capital A. Keeping inverse operations in order protects the entire solution.
Try a transfer example. A quadratic has vertex 2, negative 5, and passes through 4, 7. In standard form, it is px squared plus qx plus r. Find p plus q plus r. Pause, and decide which input reveals that sum.
Begin with vertex form f of x equals capital B times x minus 2 squared minus 5. Use the point 4, 7. 7 equals capital B times 2 squared minus 5. Adding 5 gives 12 equals 4 capital B, so capital B equals 3.
The requested coefficient sum p plus q plus r equals f of 1. Substitute 1 into 3 times x minus 2 squared minus 5. 1 minus 2 is negative 1, whose square is 1, so the result is 3 minus 5, or negative 2.
Verify by expansion. 3 times x minus 2 squared minus 5 becomes 3x squared minus 12x plus 12 minus 5, or 3x squared minus 12x plus 7. The coefficient sum is 3 minus 12 plus 7, which is negative 2.
The reusable idea is broader than quadratics. For any polynomial written as a sum of coefficients times powers of x, substituting 1 turns every power into 1. The value at 1 is therefore the sum of all coefficients.
For the source problem, the vertex gives f of x equals capital A times x minus 3 squared minus 8. The point 5, 4 makes capital A equal 3. Then the requested sum becomes f of 1.
Evaluating gives 3 times negative 2 squared minus 8, which is 12 minus 8. Therefore, the exact source answer is choice A, 4.
Use vertex form to honor the given geometry. Use the extra point to determine the scale, and evaluate at 1 to reveal the coefficient sum. Symmetry and full expansion both confirm the same result. A plus b plus c equals 4.
Optional SAT math study resources are linked in the description. If you purchase through an affiliate link, the channel may earn a small commission at no extra cost to you. As an Amazon associate, I earn from qualifying purchases.